Well, let's see some numbers, really familiar ones. And as we know, they're all along this famous line, the real line. I assume we're all really familiar with the notion of set. And the set of all real numbers are represented by this big R here. And today I want to talk about the story of real line. So here comes the first story. Once upon a time, there is a cult founded by this guy called Pythagoras. He is a famous mathematician, philosopher, and a great teacher. He's also a super cool guy that allows women to enter his classroom. But this math group or religion, cult, whatever you say it, has really weird beliefs and habits. First of all, they're all vegetarians and they believe it is sinful to eat beans, and human and animal souls are immortal. But most importantly, they believe all is number. What does that mean? They believe deep down inside everything is just number and they can all be represented by number. This belief is pretty advanced for a guy at that time. Well, in this group, people like counting pebbles, especially pebbles in the form of triangles. Well, we cannot blame them because by that time they don't even have these nice little symbols that we used to represent numbers we know today. As a matter of fact, they believe every number has its own character and meaning. For example, number 1 was the generator of all numbers. It's kind of like the Chinese belief. 2 represented opinion, 3 means harmony, 4 justice, 5 marriage, 6 creation, 7 means the 7 planets of wandering stars, etc. Well, as you and I may not be able to understand, these people are able to relate these numbers with nature, and that's why we call these numbers natural numbers. Here we say natural number starts from 1, but some may argue natural number starts from 0. It's still worth debating, but let's move on for now. Sometime later, the other side of the planet, in ancient China, this guy took few steps to the left-hand side of the real line and discovered something interesting. By that time in China, people used to borrow things from each other, like monies, sheep, cows, dogs, chicken, whatever. And that's how people discovered if I owe my neighbor 6 yuan, $6, then in my account, in my book, in my little notebook, I know now I have only negative numbers, and that's how people discovered negative numbers, negative integers. And we call these negative integers 0, and natural number we just saw, we call them integers. The set of all integers is represented by this big Z here. Going back to Pythagoras, this guy fell in love with the notion of ratio. He believes everything, like astronomy, like music, art, engineer, math, of course, is all about ratio, like P over Q, such that Q is not 0 because it doesn't make sense if you want to divide something into 0 pieces, and Q is a natural number. P is an integer. The number of this form of ratio is called rational number. See this ratio here. Let's see some more example. Like 1 over 3 points 3, and 1 over 7, 2 over 7. Can you see something interesting? Well, actually, all rational numbers are just repeating decimals. It's a fun fact, but why? Not gonna talk about this today, but it's nice to think about it. And if you were interested, I provided a proof. Going back to the real line, we see 1 over 2, which is 0.5, in the form of ratio. 1 over 4, also a rational number. 1 over 8, see what I'm doing? If we keep repeating this process, this method, we can find infinitely many rational numbers between 0 and 1. This property is called the density of rational numbers. Rational numbers are dense, means we can find infinitely many rational numbers between any two rational numbers. Well, if we want to represent every rational number as a dot on the real line, it's gonna look like this, because there's simply so many of them. Some practice question. Is -5 a rational number? Is 6 over 8 a rational number? Well, -5 can be represented as -5 over 1, which is the nice ratio form we want. Also, 6 over 8 is already in the ratio form we like, so of course both of them are all rational numbers. Going back to this real line, if rational numbers are so dense, and as Pythagoras already noticed this property, he can't help but thinking, are all numbers on real lines, are all numbers just rational numbers? Is every number so nice that can be represented into this nice and elegant form? Well, if you want to answer this question, let's talk about this theorem. Pythagorean theorem, discovered by Pythagoras, of course, and in China people call it 勾股定理. Well, it's not important that who actually discovered it or who discovered it first, but just we know in every right triangle, a squared plus b squared equals to c squared. Well, it is kind of hilarious that Pythagoras' own theorem actually proved his own belief wrong. But how does that happen? Well, he has this good student here called Hippasus. One day he was so bored and he was looking at this right triangle here. 1, 1, and square root of 2. He was thinking, is square root of 2 also a rational number? Well, what if we assume square root of 2 is a rational number that can be represented into the form of p over q? Let's assume p and q do not have any common divisors. What does that mean? Well, if that's 3 over 4, then we're good. But if that's 6 over 8, both can be divided by 2. Then we say they share a common divisor of 2. I mean, except 1, of course. This is our first assumption. And follow this equation, we have 2 equals p squared over q squared. And 2q squared equals p squared. What does that mean? On the left hand side, we have 2q squared. This 2 told us that the whole number is an even number. But as we know, an odd number squared is still an odd number. Only even number squared is gonna give us even number. So p must be an even number. This is the first fact we know. If p is an even number, let's represent p with 2a here. So 2q squared equals to 4a squared, followed by previous two equations we have. And we know q squared equals 2a squared. This looks familiar. That told us, follow the same deduction, we know that q is also an even number. See these facts we have here. If p and q do not have any common divisors, how can they be both even numbers? There must be something wrong. But what's wrong here? Well, the only thing we didn't prove is that square root of 2 is a rational number. So it must be this assumption that is wrong. We cannot represent square root of 2 with a nice ratio. Well, when Hippasus found this number, he was thrilled, excited, and also scared. And he told his mentor, his teacher, the great Pythagoras, about this number. Pythagoras was intimidated. He thinks this number square root of 2 is so sinful and so disgusting and such a disgrace that cannot even be represented by a nice racial form. Well, that just shakens his own belief. He sentenced his own student Hippasus to death just because of this number. And that's how we discover numbers like square root of 2. If we want to find it in the real line, first we draw this triangle, and by this circle we move the square root of 2 to the real line. And using the same method, we can find square root of 3, square root of 4, square root of 5, and 7, of course, whatever you want. And square root of 2 is actually equals to 1.414 whatever, which has no patterns, no repeating patterns in the decimal parts. That follows the fact I just talked about, that all rational numbers are just repeating decimals. And we call these numbers irrational numbers. That just means real numbers that are not rational numbers. And the notion r minus q here is just set minus. That means the set of real numbers minus the set of rational numbers. Of course, there are other famous irrational numbers like e and pi you may heard of. Some more practice questions. Can we find some more irrational numbers using current ones we have? Well, I already gave the answer. It's pretty simple, right? Just how about e plus 1, e plus 0.5? Any irrational number plus a rational number is still irrational because we cannot represent it into a ratio form. Okay, that's everything I want to talk about for today, and let's review everything we've learned so far. The set of real numbers are set of irrational numbers. Of course, there will be rational numbers q. Inside rational numbers, there will be integers z. And finally, natural numbers. Can we fill in this graph with every number we have seen today so far? First, square root of 2. Pi and e, they're all irrational numbers. And 1 over 2, this is a fraction number, it's a ratio. So it's a rational number, but not integers. inside integers there are negative integers 0, 1, and 2. That's great. But here are some little bit harder practice questions. If pi is defined by a circumference of a circle divided by its diameter, what do we know about circumference c and diameter d? Well, first of all, pi is an irrational number. If you're thinking about a, consider representing them both in the ratio form. If c is a over b, d is e over f, pi equals c over d will still be a nice ratio form, so it's still gonna be a rational number, but pi is an irrational number, so a is wrong. How about b? Do they have to be both irrational numbers? What if diameter is 2 and circumference is just 2 pi? Then only one of them is irrational. Now how about c? There has to be exactly one irrational number. Well, consider diameter equals to e and circumference equals to e times pi. That's right, they're both irrational numbers. So D is the right answer. There has to be at least one irrational number. How about E? Can you prove E is wrong? That's right, we already know that two of them can all be irrational numbers. That's pretty easy, right? Second one, if R is an irrational number and K is an integer, what do we know about number X equals to R to the K? A. X is an irrational number. X is an integer. X is an irrational number. D. We don't know anything about X. It's kind of like a trick question, but if you're thinking about A and B, consider X equals to e to the 1, and it's simply e, which is an irrational number. And if you're thinking about C, X equals to square root of 2 to the 2. That's 2. It's a natural number, an integer, so it's a rational number. So in fact, we don't know anything about X. Here's all for today and hope this is helpful. Thank you for watching.